Target, 800 to 1,200 words tone, conversational, storytelling, technical but accessible runtime, ~8 to 10 minute. They say week 22 was just another week in AI. But if you work in robotics, it was the week everything started to click, and also the week we got a humbling reminder of how far we still have to go. Welcome to AI Frontier Weekly. And today we're breaking down the 5 papers that define the state of embodied AI right now. One unified foundation model that does it all: manipulation, navigation, trajectory prediction. One wake-up call showing today's best robots memorize rather than understand. And one new training technique that pushed dexterous manipulation up by 33 percentage points. Let's get into it. Alibaba's Qwen team has been crushing it in vision language. But what they just released takes things to a whole new level. Qwen-VLA isn't another chatbot that can describe a scene. It's a full-on vision language action model, a single neural network that takes in visual input and outputs continuous motor commands. The trick is in the action decoder. Instead of discretizing actions into bins, which loses nuance, they use a diffusion transformer, or DIT, to directly generate smooth, continuous motor trajectories. Think of it like how image diffusion models generate pixels, but here it generates joint angles and gripper positions. Now here's where it gets really interesting. Qwen-VLA was joint pre-trained on everything: robotics trajectories from real robot arms, human egocentric video, synthetic simulation data, and vision and language navigation data. The result? 97.9% on the LIBERO benchmark. And in real-world OOD, out-of-distribution, scenarios on the Aloha platform, it hit 76.9% success. That Aloha number is the one to watch. Real-world, out-of-distribution, meaning scenarios the model never saw during training. Hitting 76.9% there is genuinely impressive. The authors call this the closest the field has come to a robot GPT moment. And honestly, they might be right. We're watching the era of single-purpose robotic controllers end in real time. But right after that high came a necessary dose of reality. Enter RoboWits, a new benchmark for bimanual robots, specifically testing cognitive reasoning and creative tool use. The setup is clever. Give a robot a seed task, hammer this nail into the board. The robot succeeds. Then mutate the task, the hammer is gone. Use this screwdriver to tap the nail in. The robot collapses. And it's not just one model. Pre-trained VLAs across the board, state-of-the-art vision language action models, succeed on the seed tasks but completely collapse on mutated tasks. That gap is massive. And it tells us something fundamental: current embodied AI memorize manipulation sequences. It does not understand tasks. This is the same lesson we keep relearning in AI. When you strip away the shortcut, when you force the system to genuinely reason about the tool's affordance instead of pattern matching, today's best models fall apart. RoboWits is the wake-up call this field desperately needed. So if our models memorize rather than understand, how do we bridge the gap? Post-training. And a paper called BORA shows exactly how effective that can be. BORA stands for, well, it's a clever acronym, and it tackles the offline-to-online reinforcement learning problem for dexterous VLA post-training. Here's the core insight: during the offline phase, you use the VLM's own cognitive tokens, the internal representations from the vision language model, to build a critic, a value function that scores actions. Then in the online phase, you bring in a lightweight human in the loop. The human watches the robot attempt a dexterous task and provides a residual correction, a small nudge, like your wrist angle is off by 5 degrees. That tiny correction is gold. The model uses it to refine its policy. And across 5 dexterous tasks, threading, grasping, rotating, inserting, manipulating, BORA delivered a 33 percentage point absolute improvement. Let that sink in. 33 points. That's not incremental. That's transformative. The lesson here is clear: the best path to dexterous manipulation isn't more data. It's smarter post-training with targeted human feedback. Before your robot can act, it needs to see, and not just see static objects, but understand motion, physics, and interaction. 2 papers this week pushed that perception layer forward. First, DynaFLIP. The problem it solves is that most vision models treat motion as a downstream task, something you do after perception. DynaFLIP pushes motion understanding upstream, directly into the perception pipeline. It trains on image, language, and 3D optical flow triplets, using a technique called simplex volume minimization to align these modalities. The result? 22.5% improvement under out-of-distribution scenarios. When the robot encounters a scene it's never seen, new lighting, new object arrangements, new motion patterns, DynaFLIP's representations hold up. And then there's PhyGenHOI, generating physically accurate 4D human-object interactions. It combines a motion diffusion model with a material point method physics simulation. Translation? You get realistic, physics-grounded 4D scenes of people interacting with objects. Pouring coffee, opening doors, picking up tools, all with proper contact dynamics. This matters not just for simulation, but for how robots learn from human demonstration. The better our simulated humans interact with objects, the better data we can generate for training real robots. So let's zoom out. What did week 22 tell us? 1. We have a foundation model moment. Qwen-VLA shows the field converging on unified architectures that handle multiple modalities and multiple tasks in a single network. The robot GPT moment is real, and it's happening in China. 2. We have a reality check. RoboWits proves that convergence on benchmarks doesn't equal understanding. These models are brilliant pattern matchers, not creative reasoners. And until we solve for understanding rather than memorization, we're going to keep hitting these walls. 3. The path forward has clear ingredients. BORA shows the power of targeted post-training with human feedback. DynaFLIP shows we need to build motion understanding into the foundation, not bolt it on later. And PhyGenHOI shows that high-quality physics simulation is the bedrock that generates better training data. The pieces are coming together. But as RoboWits reminds us, the hardest problems are still unsolved. If you're building in embodied AI, or just watching from the sidelines wondering when the robots will actually fold your laundry, this is the newsletter and channel to follow. We track these papers every single week so you don't have to. Hit subscribe, ring the bell, and join us next week as we dive into what's happening at the frontier. Until then, keep building. Visual